Intermolecular forces are the forces that exist between molecules that hold those molecules together. Keep in mind that intermolecular forces only occur in covalent compounds, because if you think about it, molecules do not exist in ionic and metallic substances. They don't have ions, they have crystal lattice structures, etc. So they only exist in covalent compounds. So let's say we have some water molecules here. We've got these water molecules we're drawing with these little Mickey Mouse head shapes. So we've got the oxygen face and the little hydrogen ears. And we can make sure we realize that when we're talking about intermolecular, we're talking about the attractive force that exists between these molecules. Within the molecules, those would be an intramolecular force that would be within the molecule covalent bonding. When I boil water, for instance, or try to melt ice, I'm not breaking apart the hydrogens from the oxygens. I'm simply breaking down those intermolecular attractive forces, sometimes referred to as IMFs, between those water molecules. So ionic, covalent, and metallic bonds are what I refer to as the rip your head off bonds, because they're not easy to break apart. So trying to get the hydrogens off the oxygens, that's hard. Breaking the water molecules apart from each other, not so much. Now, the IMFs that we're going to be talking about rank in order of weak to strong. The first one, London dispersion forces, are the weakest. London dispersion forces, also known as induced dipole, or van der Waals forces. They're known by all three, so we have to be familiar with all of those names. First of all, those are the only attractive force in our nonpolar compounds. So this is, again, the only IMF in nonpolar substances. And it's caused, as it says here, by the attraction of a positively charged nucleus of one atom for the electron cloud of an atom in a nearby molecule. What that does is induce a temporary dipole. And I'm not much of an artist, but let's imagine that we've got this xenon atom here, for instance, with its electron cloud around it, and along comes another xenon atom. And those electron clouds, okay, so it's not very scientific, but we're going to call their electron clouds gushy, or weebly wobbly. Gushy is a little easier to say. So when at any given point in time, they may be wobbled one side or the other of that nucleus. And so we end up with a more concentrated electron cloud or dense electron cloud on one side than we do on the other. And what ends up happening is that the nucleus, this positive nucleus of one of the atoms, will attract the electron cloud of another neighboring atom. Now remember, electrons, very repulsive, so what ends up happening in that situation, again, my artistic ability is not great, but we end up with a distorted electron cloud. That distorted electron cloud then ends up being polarized. I end up drawing this, and it always ends up looking like some eyeballs that are peeking out to the side of the board, but I think you'll at least get the idea of what I've drawn here, that on this side over here, where we have a more dense electron cloud further away from that nucleus, then we're going to get a partial, very tiny partial negative charge. Over here, we get a very tiny partial positive, which is attracted to the very tiny partial negative on this side of the cloud, etc., etc., etc. And again, we call this a polar, it's very tiny polarity, but it is a polar induced dipole at this point. Um, Now, when you look at elements like fluorine, chlorine, bromine, and iodine, those diatomic molecules, this is one of the things that's going to explain why fluorine and chlorine are gases, bromine is a liquid, all of this at room temperature, and iodine is a solid. So we've got fluorine and chlorine, which are smaller molecules, small atoms, and iodine much larger. What happens when we have these large electron clouds is that they are more easily polarizable. You could say they're more gushy, but that wouldn't look very good or sound very good on the AP test. So let's call it more easily polarizable, easier to move around and create these temporary dipoles. And so they're going to be attracted to each other more strongly. And because of that, you have a situation where at room temperature, the iodine molecules are going to be attracted to each other strongly enough that they're actually going to be a solid at room temperature. Fluorine's zipping around there. It's little. Its electron cloud is not very polarizable. It is going to have to get quite cold for that to turn into a liquid or a solid. So bigger atoms tend to have larger London dispersion forces. They also tend to, the bigger the molecule, have a higher boiling point. So those are the kinds of things you're looking for whenever they ask you questions about attractive forces in those nonpolar substances. Now, dipole-dipole interactions, a little bit stronger attraction. These are caused or created, I guess exist would be a better term, in molecules that are already polar. So if you've got a molecule that already has this partial positive end and a partial negative end, then it's going to be attracted to another molecule with a partial negative and a partial positive, which is attracted to another molecule with a partial negative and a partial positive, etc., etc. So you've got all these opposite charges on these ends of the molecules. Now it's just a partial charge, so it's still not, we're not talking ionic bond here with those full-blown ion charges, but we are talking about a quite strong attraction between these molecules that were already polar in nature. Now if you look at hydrogen bonding is very strong for an intermolecular attractive force. It forms between hydrogen and very electronegative elements like fluorine, oxygen, and nitrogen. And again, it forms between these because they are very strongly electronegativity, or they have very high electronegativity. Very high electronegativities. Remember, electronegativity is what I think of as a tug-of-war force between that shared pair of electrons. Fluorine, oxygen, nitrogen do not play fair. So this, again, very high electronegativity. Fluorine, oxygen, and nitrogen are going to attract their electrons more strongly than hydrogen. And so think about how hydrogen is different from every other atom. It's sharing that one electron with, let's say, fluorine, for instance. So we've got hydrogen here. All it's got is that one electron, and it's going to share with fluorine. Fluorine's got 7 valence electrons. But fluorine is pulling way more than its fair share of those electrons. So that electron for hydrogen is going to be in the vicinity of fluorine's nucleus more often than it is around hydrogen. So fluorine's going to have a more dense cloud. Hydrogen is going to have a not much of an electron cloud. Think about it. Hydrogen only has 1 electron to begin with. So if fluorine is pulling more than its fair share of that electron, that hydrogen is very electron deficient. Incredibly electron deficient. It doesn't have any other electrons to help, I guess you could say, lessen that blow. So what does it do? It starts looking around. It's very positively charged, okay? And it's going to start looking around for an electron pair to hook up with. And what comes along? Another hydrogen fluoride molecule. And what that hydrogen will do is to hook onto and form a strong attraction with a lone pair in that neighboring hydrogen fluoride molecule. Very important to remember to discuss it in those terms. You always want to mention that the hydrogen bond is the attraction between a hydrogen and a lone pair on an atom in another molecule. That's one of the things that they say people miss all the time on the test, to start discussing about how the hydrogen is attracted to its own fluorine or whatever else what other element or atom it's attracted to, and they miss the point that it's got a nice covalent bond between the hydrogen and fluorine in that molecule. It's being attracted to the lone pair in another molecule. So this is hydrogen bonding. And it's about 5% the strength of a covalent bond, so it's quite strong. And it's responsible for a lot of the odd characteristics of water. We talked a lot about that in Chem 1, about the fact that it has a high surface tension, that it has a really high specific heat. There's just lots of things that are explained for water by hydrogen bonding. So we'll talk more about that later. The last one is ion dipole. And honestly, the only time I've ever seen them mention ion dipole is when you've got an aqueous solution of an ionic compound. Let's say we're dealing with, we'll take water, for instance, with, let's say, potassium iodide. That's a good one. Potassium iodide dissolved in it. So you dissolve the potassium iodide in there, and you're going to get the potassium surrounded by water molecules, and the water molecules are going to be facing with the oxygen facing in, and you get these layers of water molecules around that potassium ion. Three-dimensionally, I can't show the three-dimensionality of it very well here, and you get the iodine being surrounded by the water molecules with the ears facing towards it, the hydrogens, that positive end of the water molecule. And again, my artistic ability is not strong, but you get the idea that those are being surrounded by those water molecules. Now think about it. This time we're not talking about just the partial charges of the water molecules, partial negative attracted to partial positive. We've got a fully charged positive potassium in this case, and the fully charged negative iodine, and those ions attracted to a dipole is the strongest of our attractive forces. So we will talk more about the properties of liquids as we move through this unit, but just some terminology for now. Vapor pressure, also known as equilibrium vapor pressure, sometimes referred to as volatility, the tendency of molecules of a liquid to escape the liquid phase and enter the vapor phase. So, tendency to vaporize. Vapor pressure increases as the temperature increases, and the higher the vapor pressure, the more volatile the liquid is. It's more likely to vaporize. Boiling point is the temperature where the vapor pressure of the liquid is equal to the atmospheric pressure on the system. And normal boiling point is when that pressure is 1 atmosphere. So you can have boiling point in a lower atmospheric pressure condition like high in the mountains that is different from normal boiling point at 1 atmosphere. So it's important to make sure you specify, if you're talking about 100 degrees Celsius, that you make sure and refer to that as the normal boiling point. The Clausius-Clapeyron equation relates vapor pressure and liquid temperature. And we also have the heat of reaction, heat of vaporization involved in this. It says to estimate the vapor pressure of water at 85 degrees Celsius. It says that we're going to note that the normal boiling point of water is 100 degrees Celsius at 1 atmosphere. And the heat of vaporization for water is well known. If you look it up, it's 40.7 kilojoules per mole. And R is going to be the joule per Kelvin mole R value. Now, before we even get started, we ought to get our units where they need to be. And since we're dealing with joules per Kelvin mole, we want to make sure and go ahead and change this to our 40,700 joules per mole. Otherwise, we're going to forget to change our units in the problem, and that's an issue that I see happening a lot on tests, is forgetting to make sure that those units match up. So at 85 degrees Celsius, changing that unit as well, that's going to be 358 kelvins whenever we add our 273 to that, and 373 kelvins for our boiling point of water, our normal boiling point. So we've got a T1, T2 situation, a P1, P2 situation. We are, first of all, going to write down the equation. Ln of P2 over P1 is equal to the vapor pressure over R times 1 over T1 minus 1 over T2. The biggest problem people have is messing up where their P1s and P2s are. So think about it. We want to know the final vapor pressure at 85 degrees Celsius. And so that vapor pressure there that we're trying to find is going to be our P2. So the 85 degrees Celsius is going, or our 358 kelvins is going to be our T2. That puts the 373 kelvins as our T1 and our 1 atmosphere as our P1. So that gives us the values that we need to plug in. So this becomes natural log of P2, which is what we're looking for, over P1, which we said was 1 atmosphere. And that's going to be equal to 40,700 joules per mole over 8.3145 joules per Kelvin mole. That's going to be multiplied by 1 over T1. T1, remember, was 373 kelvins minus 1 over T2 at 358 kelvins. We end up with a value of ln of P2 being equal to negative 0.5499. And if we take the inverse natural log, or e to the x of both sides, we end up with the fact that P2 is equal to 0.58 atmospheres. So that's the way you would work out that type of problem. Different things might be asked for, as far as, you could be given those temperatures and pressures and asked for vaporization, heat of vaporization, various ways that could be asked for. Okay, the last thing that I want to talk about is something called a network solid. We have talked about ionic compounds that are a crystal lattice structure of alternating negative and positive charges. So you've got a crystal structure of ions. We have a covalently bonded molecule structure, molecular structure, where the molecules are covalently bonded within themselves, water for instance, oxygens to the hydrogens, but between the molecules we have a weaker intermolecular attractive force. Well, there's something called a network solid, sometimes called a covalent network solid, which is a lattice structure just like an ionic compound, but this time all of those atoms are covalently bonded to one another. That is an incredibly strong attraction. You end up with things that have incredibly high melting points. They're very strong. Our best example of that is diamond. And again, it's simply a lattice structure of, instead of ions, it's a lattice structure where every carbon atom is covalently bonded to the carbon atom beside it. So again, incredibly strong.